Today we are going to be going over the instantaneous center of rotation. The first situation you're going to come across is where the velocity vectors are going in different directions, which is most cases, with one slightly more angled than the other. What you're going to do to find the ICR is draw two perpendicular lines to the separate velocity vectors, and where they intersect is going to be where your ICR is. And the two lines connecting the ICR and the velocity vectors are going to be needed for the following equations, with the angular velocity going in the direction assumed by the linear velocities. The equations are RA ICR equals VA over omega AB, and VB equals omega AB times RB ICR. The next situation is when the velocity vectors are going in similar directions and the 2 points are not exactly in the same line. Again, drawing two perpendicular lines to find the ICR. With this situation, the ICRs might be slightly farther, but still correct. And again, assuming the angular velocity based on the direction that the linear velocities are going, and the equations in a different order. The third situation, both velocities are going in the same direction, so the ICR will pretty much be on top of each other, / in a line. As you can see with the way I drew them slightly off center, you can see the two lines connecting the ICR to the velocities. The fourth situation is similar to the first, but just going in the other direction. As a note, you can use a ruler to make the ICR lines. Typically, I don't, just because I take my notes on my iPad. Also, the angular velocity direction is still guessed based on where the linears are going, with the ICR just being towards the right instead of towards the left, like seen before. Sometimes you will be lucky and find that the ICR is simple to find because one velocity is going to be going in only vertically and one will be going only horizontally. As then, the ICR is just simply going to be a right triangle, which length's easier to find using SOHCAHTOA rather than the law of sines. For our first example, we see that the pole is attached to two wheels, one moving vertically and one horizontally, with a little hang-off section. Between point A and B, the length is 4 feet, and between point B and C is 6 feet. And the velocity at point B is 1.5 feet per second in the downward direction. Trying to find the velocity at point A and the velocity at point C. Because of the way this problem is set up, we know that wheel A can only be moving in one direction. And then we're going to find the ICRs, which you can see I've already done on screen. Because this, we can use SOHCAHTOA and use the angles because of just angle rules. As you can see, we find RB is 3.625, and the omega, the angular velocity of the length is 0.4138. Then to find RA ICR, we just do the hypotenuse times the sine, and then velocity of A using that angular velocity we found and RA, which gives us an answer of 0.6995 feet per second. Because the number is positive, it just means that it agrees with the assumption of the direction we made, which was towards the right. Now, the second part of this example is to find the velocity at point C, both magnitude and direction. To start, we're going to need RC, which is done with more triangles, and the ICR is still in the same place, so the line is drawn from point C to the ICR, and here we are going to fill in what we know. The way I ended up doing it was finding the square root of the following, which was just RB plus that cosine piece and then the sine of the other piece, which you can see is a very long equation. And we're still using that cosine because that is what we know. So as you can see, the RC ICR is the square root, which is a very long value. Incredible. And it's using the Pythagorean theorem. X squared plus y squared equals c squared. and it gives us an answer of 9.411. I accidentally write the wrong number, but I will change it in a moment. The velocity using the angular velocity we already found, and then RC ICR, as you can see I'm writing the correct number, gives us that 3.899 feet per second. And then we need to find the direction of the velocity at point C. So what we're going to do is use the x and the y and the inverse tan to find that the angle of the velocity at point C will be 74.37 degrees from, I believe, the horizontal. Next two examples, you can either watch all the way through or pause after I give the knowns and skip to the timestamps told on screen. For the first example, we're given LAB, LBC, omega AB, and the angle at point A. And we want to find the velocity at C. And to start, we're going to find the velocity at point B, knowing the angular velocity and the length of AB. And we can assume the direction that V is going based on the way it's set up. So LAB equals 0.2, and then omega AB is 4 radians per second. So using our calculator, we can see that this will be 0.6 meters per second. And then to find VC, we know both the direction of VB and that VC will either be going to the left or to the right. And based on both the angular acceleration of length AB and the velocity at point B, we can assume that it is going to be going to the right. And it also is important to note the angles at point B. As you can see, there's a lot of them just because of the way the velocities are going. Now, we've labeled our knowns, and we're going to find that ICR, drawing our perpendicular lines, which will be used to find RC and RB, this time using the law of sines. To find out what we need to find, we're going to set up our equation of omega BC equals velocity at point B over RB ICR. And then we're going to find RB ICR, which, because of the angles we know, which as I'm drawing out on screen is 30 degrees at the top and then 120 at B, we know that the bottom is also 30, and so RB will also be 0.2. And because of the previously found VB, we can plug into the equation 0.6 over 0.2 to give us an answer of 3 radians per second. Now we are going to use the law of sines to find RC ICR. And the law of sines is just the sine and angle over the length equals the other sine and angle over the other length. So we know our angles and we know LBC, so we can find that RC ICR equals 0.3464 using cross multiplication and division. Then to find the linear velocity at VC, it'll be RC ICR times omega BC, both of which we now know. So 0.3464 times 3 plugged into the calculator to get an answer of 1.0392 meters per second. And depending on your teacher is what the sig figs or decimal places you will round to. Moving on to our third and final example, the same rules apply. If you want the knowns and then to solve on your own, skip to the timestamp on screen. We know that theta is equal to 40 degrees. Wheel B is moving upwards at 1.5 feet per second, and the length between points A and B is 5 feet, and then between points B and D is also 5 feet. And we want to find the angular velocity of the door and the velocity at point D of the door, that free end. As you can see, this is very similar to our first example, just with a bit more context and going in a different direction with different angles. To start, we're going to be drawing our free body diagram of the door without all of the extra nonsense, otherwise known as the walls. And we are going to be putting in what we know, which is that angle, the direction we assume the door is going in based on the velocity of point B, which is in the upwards direction. And because of this, we can assume that VA will be going towards the left. And again, making a nice right-hand triangle to find our ICR, we can find RA and RB. You can use either angle, the angle given of 40 degrees, or you can find the other angle of 50 degrees. And I use the 50 degree angle because it makes more sense in my brain for RB to be using the cosine and RA to be using the sine. Completely up to you which angle you use. Just make sure you keep it all straight, because if you were to use 40, RA would be using the cosine 40 and RB would be using the sine 40 based on how the triangle looks. So because I'm using that 50, we can do 5 times sine, after all explaining all that, 5 times cosine 50, and then to equal 3.213 meters, and then do the same thing for RA and find the answer to be 3.83 meters. Make sure you're keeping your angles and your units straight, because that will help you a long ways. Now, because we're going to need it later, we're going to find RD now. And I'm sure there's easier ways to do this, but I found it using a bigger triangle, using the full length of the door at 10 feet, and finding either side, and then subtracting RA from that total length to find just the small triangle we need. As you can see, I'm drawing a little separate triangle just to keep everything in order. And we know that bottom angle because we know the other angle. So because of that, we get 6.427, which we will use when we use the Pythagorean theorem to solve for that hypotenuse. And 7.66 minus that RA is just 3.83. We don't need that angle. Don't know why I put it. I think I forgot that I can just use the Pythagorean theorem at this point. Which we do, which is, as a reminder, a squared plus b squared equals c squared. My favorite equation that is forever ingrained in my brain. And we will be able to find that RD is equal to 7.481 meters per second. Meters. Sorry, I can't read. This is why you need to keep your units straight. And then to find this angular velocity, you are going to use the equation W ABD, or omega ABD, because it's the total door, because it's 1 unit, which is just, I noted this down just in case you were to solve it using a different method, like the 3 diagram method or something else, just that one is only going in one direction and one is only going in the next. We don't need it here though. I think it was just in my notes. So again, omega ABD equals VB over RBICR. Again, not quite needing that RD yet, but we have it now for when we need it. So 1.5 over 3.83 to give an answer of 0.4668 radians per second because it's angular. And we assume that direction because it was positive and agreed. So now we can just easily find VD using that angular velocity we just found times RD, which we found at the start, and plugging that into the calculator will give us our answer of 3.492 meters per second. Okay, so this is for the pistol crank mechanism explored in dynamics. And so we have the basic clear, control, close all. And then I made it so through a little bit of ChatGPT's help and my own knowledge from a previous class, I've constructed this simulation in MATLAB just because that's what I'm more comfortable with. And so we have it ask for the user for inputs, the crank length, rod length, and constant angular velocity. We then have it do the velocity and acceleration analysis using the givens, and then we're also plotting the position, velocity, and acceleration, and then have a little animation. So if I run this, enter crank length for rod length, and if I did something that was less than C, it would give me an error and have me redo it. Same if you just type something in wrong. So I'll have it, just to show you, I'll have 3 and then give you a 3.5. Connecting rod length must be greater. So then we have to rerun it. So 3, 7, and then 2.7 or 2.9. So then we get this figure, and then we also have another figure that is this. So as you can see, this is what everything looks like. And now you can go out and use this to find the ICR in real life. Have a good day, and thank you for watching.